All right, last lecture before the exam, also on new material, chapter 15, chemical kinetics. Last time we talked about some of the basics, and we're going to continue talking about the basics. This time, as before, this is all stuff, including today's lecture, that I think everybody's seen before, but it's good to go over it anyway because it's so fundamental and basic, and also because for some people, I'm sure it's been a long time since they've seen it. So we talked about rate laws and rate equations last time. And this time, we're going to talk about what happens when you set up a rate equation and then solve it. It's a differential equation, and you can solve it in order to get the time course, the full time course of a chemical reaction. So let's take the very simplest case, a first order reaction. If the reaction is an elementary reaction, it'll look like this. It'll have a single reactant going to some set of products, and it doesn't matter what the products are. The rate then is equal to, according to one definition, right, minus dA dt, the rate of change for A. It's also equal to, according to the rate law, a rate constant K times the concentration A. That's a first order rate law. That's what makes this whole thing first order. Well, if these two things are both R, then they're both equal. That means you get that minus dA dt is equal to Ka. That's a closed differential equation. We can solve that differential equation for the concentration of A as a function of time. Let's do that. We're not going to do this a whole ton, but it's good to do it in this very simplest of all possible differential equations, really. We have that minus dA dt equals Ka dividing through by, on both sides by A. You get dA over A, and multiplying through by dt is equal to minus K dt. Now we integrate both sides from the initial concentration at time 0 up to whatever the concentration is at some arbitrary time. And that's equal to t on this side. Integrating dt from 0 to t is equal to t. So minus kt on that side. And then the integral of dx over x is equal to log x. And so with a little bit more algebra, this becomes either of these two equivalent forms. One says that the logarithm of A is equal to the logarithm of the initial value of A minus kt, and then solving for A itself rather than logarithm of A gives A is equal to the initial A0 times e to the minus kt. In other words, what it's saying is that the concentration of A decays exponentially with time, and there is a decay constant, and that decay constant is the rate constant itself. It's a curve, if you plot it, that looks like this: concentration on this axis, time on this axis. It says that since A is a reactant, of course, it's going away with time. It's going away exponentially with time, which means that as time goes to infinity, it eventually dies out completely. But you can't say too much more, and also I guess it's worth pointing out that yes, when t is equal to 0, then the concentration is A0. You can see that in the formula, right? When t is equal to 0, this is a 1. All of this is a 1, I mean. You can't say too much more about it. I just drew this curve by hand. In fact, it's probably not very close to a true exponential. All you can really say is that it's a decaying curve. But it turns out that exponential curves like this have a property that is very useful. We'll use it, in fact, in a minute. And that property is that if you wait a certain amount of time, and that time is t1/2, a half-life time, then the concentration will have dropped by a half. That's by definition. You wait until the concentration drops by half, however long that took, that's the half-life. But what's unique about an exponential curve is that if you wait the same amount of time again, so another 1/2, so the total time is 2 times t1/2, then it will drop by another factor of 2, by another 1/2. And if you wait the same amount of time again, it'll drop by another factor of 2. So by the time you've waited 3 half-lives like this, it's dropped to 1/8, 2 to the third of its original concentration. The fact that all these half-lives are the same, that it doesn't matter the fact that you started at this point with already only half the concentration that you started with, and you started at this point with only a quarter of the concentration, it still took just as long to drop by a factor of 2. That's a unique property of a first-order process, first-order reaction. We can solve for what this half-life time is in the following way. We know that A up here, A is equal to A0 e to the minus kt. So A is equal to, we want the half-life, so we set it equal to half the initial value. That has to be equal to A0 e to the minus k when t is equal to t1 half. Taking the logs of both sides, log of a half is equal to minus, and dividing out these A0s, minus k t1 half, and so the half-life is the logarithm of 2 divided by the rate constant k. That means, notice that there's a close relationship between the half-life and the rate constant. They're basically inverses of each other. The logarithm of 2 it's useful to know, has the value of 0.693, so this is really 0.693. 0.693 and then some extra digits out here divided by k. And what that means, basically, is that apart from this constant, yeah, the half-life and the rate constant are basically inverses of each other. The faster the rate constant, the smaller the half-life. That makes sense, right? The less time it takes to drop by half. And the smaller the rate constant, the longer the half-life, and so on. And also notice, yes, that the half-life doesn't depend on the value of A0. You could see that happening in the algebra up here. The initial concentration divided out, and from that point on, it's not even in the equation anymore. Yes, and then you can also, of course, invert that and solve for, if you know the half-life, you can solve for the value of k. And so, yes, knowing the half-life is basically equivalent to knowing the value of k, and likewise, knowing the value of k is basically equivalent to knowing the half-life. So let's do an example. Let's suppose that we have some unknown reaction. We don't know what it is, don't know anything about it. A good one would be the decay of caffeine in your body. You drink a cup of coffee, caffeine goes into your bloodstream. How long does it take for that caffeine to go away? It turns out that that's roughly a first-order process, but how would you know that? You don't know what's going on inside your body. In fact, a lot of complicated things are going on inside your body, metabolizing that caffeine away. So we don't know what the order is, but we do know this. We measure how long it takes for the whatever, the caffeine or whatever, to drop by a factor of 2, right? It's gone from 1 molar to half molar. That took 2 seconds, so that's obviously not caffeine. Caffeine takes about 7 hours to drop by half. It's got a half-life of about 7 hours, and it is roughly first order, by the way. And then we wait a little longer to see how long it takes for it to drop by half again to 0.25 molar, and that takes another 2 seconds. And we ask, what is the order of the reaction? What is the rate constant? What will A be at 5 seconds instead of 4 seconds? How long will it take to reach a concentration of 0.1 molar? We can get all that information from this little bit of experimental data we have up here. First of all, what is the order of reaction? Well, the half-lives are the same, 2 seconds and 2 seconds again. We could do a third one just to make sure, but this is enough for us to at least tentatively say that's a first-order reaction. Only first-order reactions have this property of equal half-lives. What's the rate constant? Well, the rate constant, so I'm answering them down here. The rate constant is equal to 0.693 log 2 divided by the half-life. The half-life is 2 seconds, so half of 0.693, 0.347. Notice the units, seconds to the minus 1, right? You can see the seconds to the minus 1 units coming out naturally from our formula, and therefore we have confidence that we're doing everything right. Third question, what will A be at 5 seconds? Well, now we know the value of K. So we can use this formula. A is equal to the initial concentration, 1 molar, e to the minus K times time, and putting in that numbers into the arithmetic gives us 0.176 molar. So a little bit less, right? This is a little bit longer than 2 half-lives, and this is a little bit less than 1/4 of a molar, and so that makes sense. And the last part, how long would it take to reach 0.1 molar? It's going to take a little longer than 5 seconds. We can see that already. That just means solving for the time here, right? So we take log of both sides, we divide through by minus k, and we get t is equal to minus 1 over k log of a over a0. A at the time in question is 0.1 molar. Initial A was 1 molar. K is 0.347, and that gives us, notice the minus sign here goes away because this logarithm is of a number less than 1, and so it's also negative. That gives us 6.64 seconds, which makes sense, right? It's a bit longer than our 5 seconds up here. All right, that's the first order case. Now let's consider the second order case. If this were an elementary reaction, the second order case would correspond to this reaction. Two identical A molecules collide with each other to produce some set of products that don't matter. The rate constant, or the rate law that it's associated with that, is K times A squared, notice. And that's equal to minus dA dt. The 2 up here in the exponent is what makes this overall thing a second order reaction. Even if this were something more complicated, let's say A plus B plus C goes to products, so it doesn't look like a second order reaction, right? When you're looking at the reaction itself, as long as this really is the rate law, I don't know how this rate law would come about from that reaction, but suppose it did. I mean, it's perfectly possible for it to do that. It would be a complicated thing for it to happen, but we'll talk about that later. Anyway, as long as this is the rate law, then this is a second order reaction. The reaction itself isn't really relevant to whether we count it as second order or not. It's the rate law that determines that it's second order. All right, so again, we solve our differential equation. We divide both sides through by, we divide this side through by a squared, and we multiply through by dt. So we get dA over a squared is equal to minus k dt. Integrate both sides, minus kt on that side. This integral on this side, the integral of dx over x squared is equal to minus 1 over x. So that's what's happening here. We're getting minus 1 over a evaluated between a0 and the final a. And that gives us, yeah, these two forms for the second order integrated rate equations. 1 over a equals 1 over a0 plus kt, or a is equal to 1 over a0 plus kt. Again, if you plot that, I mean, we'll talk more about these in a second, but if you plot these, this one especially, A versus time, then again you get a decaying curve, and at time equals 0, of course, the A concentration has to be the initial A concentration, A0. Can you tell that it's not first order? Can you tell whether it's first or second order from this plot? Well, somebody really, a real pro might be able to, but this is a hand-drawn curve. There's no way to tell. Even if it was an officially plotted curve, you might be able to tell if you're careful enough, but not from a hand-drawn curve like this. So how do you tell? Well, we'll come back to that. There's a test that at least allows us to distinguish between first and second order cases. The first and second order cases are by far the most common cases. If you don't know anything, not even the first thing about a chemical reaction, and you have to guess out of the blue, guess that it's either first order or second order. Actually, probably guess that it's second order. That's even more common, really, than first order. All right, let's do another example. Let's suppose we have these data. T is equal to 0. A is equal to 0.1 molar. So we start with 0.1 molar concentration. After 5 seconds, it's dropped by a factor of 2. After 10 seconds, it's dropped down to 0.033 molar. Notice that this is a 5-second gap, and that's a 5-second gap. But it hasn't, and it's gone down by a factor of 2 in the first gap, but it didn't drop by a factor of 2 in the second gap. This would have to be 0.025, right, for it to have halved itself again. So is this a first order reaction? If the reaction is second order, what's the K value? Is the reaction second order? Can you really tell or not? What is the value of the concentration at 20 seconds? How long will you have to wait until the A concentration has fallen to 0.01 molar? So first of all, for the first one, I just pointed out, of course, that these two time intervals are equal, but they're not two half-lives. That means the half-life depends on concentration, right? Half-life is slower on this second step because the concentration started out at a lower value here. And that's a diagnostic for it not being first order. It doesn't tell you that it's second order. It just tells you that it's not first order. So the two half-lives are not the same. The two half-times, if you like, are not the same, and so it's not first order. If it's second order, what's the K value? Well, I solve this to get the value of K. It's 1 over A minus 1 over A0 divided by the time. Plugging in, I get 0.05 minus 0.1 divided by 5 seconds. I'm only using part of the data, right? I'm just using these first 2 points. I could use these second 2 points, or I could even use the first and third point. I'd get the same answer all 3 ways, at least an equivalent answer. Oops, I somehow messed things up. Let's go back. Yeah, here we are. But in this case, I get 1 over 0.05 is 20, 1 over 0.1 is 10, so 20 minus 10 over 5, that's 2. 2, notice the units. This has units of molar, so there's molar to the minus 1 on top. This has units of time, so it's seconds to the minus 1 altogether. Molar to the minus 1, seconds to minus 1. That's, of course, the characteristic set of units for a second order reaction. Of course, that doesn't tell you it's second order because we assumed it was second order when we were doing all of this. So all this is doing is telling us that we're getting a set of units on our rate constant that's consistent with the original assumption. Doesn't tell us it really is second order. So if it's second order, and if we now know the apparent second order rate constant, then at t equals 10 seconds, do we get the right answer, right? We've got a rate constant now. If that rate constant is right, and if it's second order, then we better get this value for our second set of data here. And let's see if we do or not. So what we want is that at a time of 10 seconds, so here's how A depends on time. At a time of 10 seconds with a rate constant of 2 molar to the minus 1 seconds to the minus 1 with an initial value, A value of 0.1, we get, this is 1 over 0.1 is 10, 2 times 10 is 20, so the sum of them is 30, we get 1 over 30, and that's 0.033. So it agrees, at least as far as we can tell. I mean, this is not very much data, and if there were any kind of experimental noise or anything, we'd want more data in order to really nail things down, because this is probably not enough to really establish firmly that it's second order. But at least given the limitations of this problem, yeah, it's second order. All right, then, next question was, what is A at 20 seconds? We now know the order and the rate constant. What is it at some longer time? Again, we just use our integrated rate law. So it's 1 over 0.1 plus 2 times 20 seconds now. So that's 10 plus 40, so that's 1 over 50, that's 0.02 molar. And finally, how long does it take to reach 0.01 molar was the last question. So now we're solving for time here using this. And so time is equal to 1 over A minus 1 over A0 divided by K. And that's the concentration we're after is 0.01. And so 0.01, that's 100, right? Minus 10 is 90 divided by 2, and that's 45 seconds. Notice again that the units all work out. All right, that's the second order case. Now, I mentioned above that it's kind of hard to tell by eye whether a curve like this is first order or second order. Is there, and we see one way to test here whether something's first or second order. Is there a sort of better way, especially if we have experimental data, a lot of experimental data and maybe some data with noise in it? It turns out there is. For the first order case, this expression is the first order integrated rate law, where we're solving for log of A instead of A itself. And if you look at it, you can see that it's in the form of a straight line if we were to plot the log of A versus time. Because We identify y, the thing we're plotting on the y-axis, with this. We identify the x-axis with time, so that just means there's time on the x-axis. If we do that, then this would be the slope and this would be the intercept in our standard equation for a straight line. And what that means is that if it's first order, and if we plot log of a versus time, we should get a straight line. If we don't get a straight line, it's not first order. And the intercept of that straight line is the logarithm of the initial concentration, and gives us the initial concentration. And the more interesting thing usually is the slope, which is equal to the negative of the rate constant. So we can, even if we have noisy data where it's not obvious what the rate constant is, we can get sort of an average rate constant by fitting to a least squares fit to the data, say, and then the slope of that fit will give us the good value of the rate constant. Again, you only get a straight line when you plot log a versus t if it's first order. If it's any other order, you won't get a straight line. There's a caveat on that, though. Sometimes it's not so easy to tell if it's a straight line or not, but we'll talk about that below. For a second order, doing the same kind of thing, I have that 1 over a is equal to kt plus 1 over a0. That's another form for the integrated rate law, of course. And again, if I plot 1 over a now on the y-axis, time on the x-axis, then that's the slope. It's k itself, and that's the intercept. And so we should get, again, a straight line that has a positive slope in this case, because k has to be positive, with the intercept equal to 1 over the initial concentration, and the slope equal to the rate constant itself. The slope just is the rate constant, nothing tricky at all about it. Again, if you plot 1 over a versus t and you get a straight line, that only works if it's a second order rate law. It doesn't work if it's first order, it doesn't work if it's 1/3 order, it doesn't work for any other order. These two plots are diagnostic for first order and second order respectively. If they fail, if you get a curved thing, it doesn't tell you what the order is. It just tells you it's not first order in this case. And if this case, you do this case, it tells you it's not second order. If they both are curved, then it's some other weird order. All right, let's do an example. For reaction, A plus B goes to products. And again, the rate laws are not always simply related to the type of reaction. So the fact that it says A plus B goes to products doesn't tell you really anything here. We get the following data. So we measure at 6 different times, and we get that the A concentration is 1 molar, 0.8, 0.67, 0.57, 0.50, and 0.44. And we want to know what is the order of the reaction and what's the value of the rate constant. Well, I don't know the order of the reaction. I don't know a test if it's some weird order, but I do know a test if it's either first or second, and those are by far the two most common cases, so that's a good guess. So let's calculate what we need to test whether it's first or second. I take logarithms of all these numbers, and then I take 1 over all these numbers and get these two columns of data. So those are all the logs, those are all the 1 overs of those numbers, and then I plot versus time. And I have both plots on top of each other here. The axis for this curve is this one over here. The axis for this curve, or the scale for this curve, is this one over here. And you can see, and you can even see it in the data here, right? 0.25, 0.25, 0.25. I mean, it's pretty obviously second order. And you see that in the very straight line, dead straight, perfectly mathematically straight line. You will never get data like that in real life. This is obviously fake. You can see that it's a dead straight line. So clearly it is second order. To confirm, you can verify that it isn't first order. But here's the thing I was saying earlier. Okay, it is curved. You can see it, but it isn't very curved. Let's suppose there was some noise in these data. You know, you probably couldn't tell if it's curved or not. So this test isn't always perfect. It depends on how good your data are. If the data are really good, you can always tell. If the data aren't so great, you can't necessarily always tell. All right. So from the plots, obviously it's second order. And again, yes, it's second order in this perfect data, but real data might not be able to tell. What's the rate constant? Well, since it's second order, we just need to take the slope. I take the slope starting from this point, going to this point, and since this is perfect data, I don't have to take a least squares or anything like that. You should, if it were real data, we should take a least squares fit or something like that, but let's not bother with that now. Oops. And so it's 2.0 minus 1.25, that's delta y, over delta x, which is, 4 minus 1. And so we get, is that right? 2 minus 1 point, that's 0.75 divided by 3, yes, 0.25 molar to the minus 1 seconds to the minus 1. All right, and that is enough for a Friday on the day before an exam, so we'll stop there.